Okay, so in these diagrams, what you need to be doing is you need to be drawing the free body diagram of the scenario, adding in your force vectors, and solving for the missing piece of information. So in this one, they said Sandy kicked SpongeBob to the right with 31 newtons of force. Friction acted on SpongeBob with 4 newtons, which would be in the opposite to the direction of motion. So friction force is 4 newtons to the left. The applied force would be 31 newtons to the right. And they said that he's going to be moving at an acceleration, or he's accelerating at 6 meters per second squared. Okay. Accelerates at 6 meters per second squared. What would the mass be? Okay. So mass here, using Newton's second law, which is F net is equal to mass times acceleration. If I'm looking for m, I have to get rid of the a, so it'd be F net divided by a. So m is equal to F net divided by a. We already have a as 6 meters per second squared. What don't we have? We don't have the net force. So since they explained to us that he's not moving up or down, right now the weight and normal force on him do not matter. So what we're going to be doing is literally just taking these two opposing forces. And what do we do if we have two force vectors in the opposite direction? We subtract. So 31 minus 4, 27. So that 27, it would be 27 newtons to the right. That is your net force. So F net would be 27 newtons to the right, 6 meters per second squared underneath. So he would have a mass of 4.5 kilograms. So you needed to make sure that you solve for the mass, and you need to make sure also that you have a correct free body diagram. Now, if we wanted to go add a smidge extra just to see where we are, okay, what would the weight of SpongeBob be? FG, what would it be if his mass is 4.5? Correct. So FG, mass times gravity. We're using, 10 for G. 10 meters per second squared is our gravity. So the weight would be mass times gravity. So 4.5 times 10 would give us 45 newtons downward. And again, since he's not moving up or down, you would have to have a force equal and opposite to that, in which case would be our normal force, and that would also be 45. And I could just put the little equal signs here to show that those two are balanced. All right, so next one, number 2. Pearl pushes a Krabby Patty across the table with 16.2 newtons of force. Friction pushes back with 3.2. Okay, so we'll draw in number 2. Draw your square. And what do we have? We're going to have a force vector of an applied force of what? Now, they didn't necessarily give us a direction, in which case you can arbitrarily pick it. I usually go that the applied force to the right, and friction would be the opposite direction of that. So I would draw a right arrow, applied force, FAPP, of 16.2 newtons to the right, and then friction of F sub F of 3.2 newtons to the opposite direction, and an acceleration of 2.7 meters per second squared. How much does the Krabby Patty weigh? Aha. Okay, so guys, when it asks for the weight, what do we do? 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 what they really want then is Fg. All right, remember, Fg is weight. And what is weight equal to? Mass times gravity. I wrote just up here before that we're going to use 10 for G. So we don't know what M is, but we know that G is 10. So what do we need to find now? We need to find mass first. So it's going to be just like what we did in problem 1, and then just another little addition to that. So M, first we got to find that, and M will equal F net over A. F net would be what? 16.2 minus 3.2, and 13 would be correct. So 16.2 minus 3.2, because they're in opposite directions, so we subtract those forces. 13 newtons to the right. So we're going to have 13 divided by an acceleration of 2.7, and we're going to get a value here of 4. It comes out to be 4.814, so we'll just call it 4.81 kilograms. Am I done? No, not done yet, because we need to take this and substitute it here for M. So 4.81 times 10. Yep, 48.1 newtons. And so let's just add that to our drawing. What direction does Fg go down always? Straight down. So we're going to have a down arrow. Fg, 48.1. Now, would this drawing be complete then? No, and why? Yeah, because they're accelerating this direction, right? They're accelerating in the direction of the net force, because in the problem they didn't say that they were accelerating upwards or downwards. We have to make sure that the up and down balance. So this would be normal force, F subscript capital N, and it just has to be the same value as your Fg. So I just put a little equal lines like that, so that my up and down are balanced. So we have our complete full body diagram here, and our actual full answer which they needed. Now there was two extra steps. Then actually not really. We pretty much did the exact same thing in part 1 because I added that little extra. So ain't no thing. All right, the pull force from the cable is pulling 400 newtons. Gravity is pulling Patrick down at 235. His mass is 24 kg. What is his acceleration? Okay, draw the free body diagram for what's occurring. All right, so right now, looks like Patrick is getting pulled straight up. So is there any forces that we see or are explained in the problem going into the left or right direction? No. But what is being explained is that he's getting pulled upward at... Thank you, bud. All right, what is happening is you're getting pulled upward at 400 newtons. All right, that would be the tension from the cable. So we'll call that Ft for tension. Said you're getting pulled at 400 newtons upward. and that gravity was pulling Patrick down at how much? 235.
He's 235 pounds.
No, newtons. Newtons. So 235. Well, according to the problem. So gravity pulling him down at 235 newtons. So that's Fg. And they said that the mass of this guy was 24 kilograms. What did they want? What is his acceleration? Okay. So A. Newton's second law is F net is equal to mass times acceleration. If I want A by itself, I would have to do what? Divide both sides by m to get rid of that. So A would just be equal to F net over m. So we're going to just rewrite that real quick. A F net over m. Do we have any of those values right now? Yes, we do. We have the mass of 24. So what don't we have? F net. So how do we do that? Where there was no other force vectors added here or on here, so you have only these two forces. You have tension going up and gravity, right, his weight pulling down. So we're going to subtract them since the forces are in the opposite direction. So F net would be 400 minus 235, which comes out to be 165 newtons. And in what direction is the net force, guys? Up. So we're going to take 165 and we're going to divide that by 24. And this would give us an acceleration of 6.875. Exactly. So usually I'd say around to 2 decimals, but when it comes out like nice and clean like that, I use all 3. So this would be the acceleration. What is the unit for acceleration? Meters per second squared. Yes. And then the other, I think the little bonus question was, is he speeding up or slowing down? Well, what direction is the acceleration? Oh, how do I know the acceleration's up? Because that's the direction of the net force. If the net force is up, the acceleration is up. And would you say that he's speeding up? Yeah, speeding up. All right, so we have our acceleration, sweet, and we have our fully completed free body diagram. All right, Squidward, playing his clarinet. He has a normal force from the floor that pushes up on him with 333 newtons, and gravity pulling him down at 333. So your free body diagram, Fg should be down at what? 333. And then Fn should be up at also 333. All right, they gave him his mass here. They gave us a mass of 34 kilograms, and they wanted acceleration. So this is what we should have. Now it just says he stands there playing the clarinet. He's standing, he's not walking, he's not pushing anything. So these are the only two forces acting on him. They gave us a mass. Acceleration they wanted. Well, what is the equation for acceleration? F net over m. We have m of 34. So what would we need to solve this? we would need the net force. But guys, real quick, just looking at the two force vectors, what is the net force?
0.
Yeah, right, because 333 minus 333 equals 0. So 0 divided by anything is 0 meters per second squared. He's just standing there. Cool? Excellent. Now, the other assignment that I'm going to have you guys do is there is a on Google Classroom there is a forces walk around. All right, so I didn't print the pictures up so for you guys to actually walk around and do that, but go to Google Classroom, you can grab a Chromebook, you can use the homework from last night, you can use this assignment to help you with those. All right, everyone must complete it. It's going to be talking about basically, there's going to be a couple questions with free body diagrams like this and maybe asking you for acceleration or mass or FNet, and then it's going to also give you just a couple examples and explain, going to ask you what law would that be. So based off of the last couple of days and the notes, you guys should have absolutely plenty of time to finish as long as you're working. All right, so if you guys go get right to it, you could probably finish this in like 10 to 12 minutes and then have the rest of the time to chill. All right, so let's get to it. I was originally going to collect it. I'm going to just come around and